Welcome to this video tutorial from SPSSVideoTutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a logistic regression in SPSS. In this example, we will explore how well 5 variables predict whether people report having problems sleeping. The 5 predictive variables in this analysis are age, gender, hours of sleep per weeknight, problems getting to sleep, and problems staying asleep. Now, before you begin your logistic regression, you want to make sure that your dichotomous variables are coded 0 and 1, or dummy coded, where 0 is the absence of the characteristic, or no, and 1 is the presence of the characteristic, or yes. Okay, this will make interpreting your results much easier. Okay, so for example, we have trouble staying asleep. We said 0 was no and 1 was yes. For trouble falling asleep, again, 0 is no and 1 is yes. And problem sleeping, 0 is no and 1 is yes. Okay, for gender, we did 0 female and 1 male. Okay, now obviously that doesn't apply for gender because there is no presence of the attribute. Okay, so but still you need to code your dichotomous variables 0 and 1. All right, now to begin, we go to Analyze, we go to Regression, we go down to Binary Logistic. The first thing that we do is we move our dependent or outcome variable into the dependent box. Okay, so problem sleeping is our dependent variable. Okay, next we move our independent or predictor variables into the covariates box. So for this example, it's going to be sex, hours of sleep per weeknight, problem staying asleep, and problem falling asleep. Okay. Now, under method, we're going to make sure that this is enter. And then next, if we have categorical variables as our independent variables, we go to categorical. Okay. And what we want to do here is we want to move our categorical variables, whether they're dichotomous or multiple categories, into the categorical covariates box. So we're going to move sex, problems staying asleep, and problems falling asleep. Okay. Then what you're going to do is you're going to make sure that contrast is at indicator. Okay. You can change this if your professor recommends a particular contrast, but we're just going to leave it as indicator. And we're going to change our reference to first. Okay, so we're going to change our reference to first for each one of these. And what this means is this: our reference comparison is going to be the first category. So for gender, it's going to be females. So we're going to highlight that and click change. For trouble sleeping, the first category is 0, obviously. So, and that's no trouble sleeping. So we're going to click change. And then trouble falling asleep, again, we click change. And we should have first after all of our variables. Next, we go to continue. We go to options. And then we want to select classification plots, Hosmer-Lemeshow, goodness of fit, case-wise listing of residuals. And we also want to select the confidence interval for the exponentiated standard coefficients, or the odds ratio. And then we click continue, and then we click OK. Okay, so the first table that we see is the case processing summary table. This tells us the number of cases included in the analysis, the number of cases that were missing from the analysis, and the total number of cases in the entire sample. And it also gives us the associated percentages. You want to make sure that if you have a high number of missing cases, that you go back and look at your data to ensure that there are no significant errors. All right. The next group of tables are the dependent variable encoding table and the categorical variables coding table. This shows you how your dichotomous variables have been coded. Okay. Whenever you run a logistic regression, your dichotomous variables always have to be coded 0 and 1. Now, we did this earlier on in our data file. However, if you begin this analysis and you have not coded your dichotomous variables as 0 and 1, SPSS will do it for you. Okay? So it's very important to pay attention to these tables because they're critical in helping you interpret your results. Okay? The next section, labeled Block 0, contains the predictive results of your analysis without any independent variables included. Okay? This is sometimes called the constant-only model or the reduced model. This will serve as the baseline for comparing our full model that includes all of the independent or predictive variables. All right? Now, the classification table shows us that the Block 0 model correctly classified 58.9% of the cases. Now, to get 58.9%, the baseline model selected the category of the dependent variable with the largest number of cases and assumed that everyone is in that category. Okay? So, since there were more people that stated they didn't have a problem sleeping, 172, compared to those who said yes, which was 120, SPSS guessed that all people did not have a problem sleeping, and as you can see, it was right 58.9% of the time. Now we want to see if adding the independent variables improves our prediction accuracy. Now, this just gives you some basic statistics about the constant only model, not important. This just tells you the variables not included in the equation, not important. Now we go to Block 1. It contains the full model with all of our independent variables. The omnibus test of model coefficients compares how well this model performs compared to the baseline model, Block 0. Specifically, it shows the results of the chi-square test of goodness of fit. If the significance value or the p-value in the row labeled model is less than 0.05, then the Block 1 model is a significantly better predictor than the Block 0 model. So we see that in this case, our model is a significantly better predictor than the Block 0 model. Okay? Now, the model summary table tells us the amount of variation in the dependent variable explained by the model. So in this case, 27.6% to 37.2% of the variability is explained by our model. Okay? Now, these are sort of pseudo R-squares, and the reason they're sort of referred to as pseudo R-squares is because they don't follow the same assumptions as the general linear model regressions. Okay? The Hosmer-Lemmischau is another goodness of fit test, and it tells us if our model is a significantly better predictor than the Block 0 model. Okay? Now, significant values greater than 0.05 mean that the model is a better predictor than the Block 0 model. Okay? Now, this is contrary to what we typically see where p-values less than 0.05 are significantly different. So for Hosmer-Lemmischau, it's the opposite. If your p-value is greater than 0.05, then there's a significant difference. All right? So this mirrors the results of our omnibus test above. Now, we go down to a very important table, which is the variables in the equations table. This tells us which of our independent or predictor variables make a significant contribution to our model. So we have the B, which you would see in a regression. You have the standard error of the B. You have the wall test, which is conducted to determine if the predictor variables make a significant contribution to the model. You have the degrees of freedom, and then you have the significance value of the wall test. Okay? If this is less than 0.05, then that means that the independent or predictor variable makes a significant contribution to the model. So we see that hours of sleep per week, trouble staying asleep, and trouble falling asleep all make a significant contribution to the model. Next, we see the column labeled exponentiated B, or the exponentiated standard coefficient. And this basically tells us the odds ratio for each of the independent variables. Okay, so said another way, the odds ratio is the change in the odds resulting from a unit change in a predictor. Okay, now scores between 0 and 1 indicate an inverse relationship between the dependent variable and the predictor or independent variable. Okay, so think of in terms of less likely. All right, scores above 1 indicate that there is a positive relationship between the predictor and the outcome variable. All right, so think in terms of more likely. All right, so the way that you would interpret the data below is as follows. So let's start with hours of sleep per week. Now, for every 1 hour of sleep per week you get, again, it's a unit change, and 1 unit is 1 hour. For every 1 hour of sleep per week you get, you are less likely to report having a sleep problem. Now, you're less likely because, again, 0.643 is less than 1. It's between 0 and 1. So it's always less likely. Now, if we go to trouble staying asleep, that is a dichotomous variable. So 0 was coded as no problem staying asleep, and 1 was coded as problem staying asleep. So since the unit change is 1, then we speak in terms of people with problems staying asleep. So the way that you would interpret this is as follows. People who have problems staying asleep are 7 times more likely to report that they have a sleep problem than those who do not report problems staying asleep. Okay? Now we go to trouble falling asleep. All right? Again, since it's dichotomous, you're going to use the category that refers to 1, or the unit 1. Okay? So people who report that they have a problem falling asleep are 2 times more likely to report that they have a sleep problem than those who do not report problems falling asleep. Okay? Now, when we go down to the last table, this indicates the cases in your sample where the model does not fit well at all. Okay? It displays cases that have a z residual value above 2.0. Okay? Now, if your z residual values are greater than 2.5 or less than negative 2.5, the specific cases should be examined for possible errors. All right? Now you know how to perform and interpret a logistic regression. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from spssvideotutor.com. Thank you for watching and much success with SPSS.